Thank you very much for giving me this opportunity to share some thoughts about needs for various models at various scales and the complementary need for lots of data from different sources. I have put up a long title to allow me to walk down to the podium. I will show this example from a Svalbard fjord and coastal area, which is where I mostly work. But I think it's a quite general example that would be valid in the Antarctic or any coastal area, more or less. What you see on the left-hand side is the model domain of a regional model that we have for the North Atlantic and the Arctic Ocean. And very prominent here is the warm Atlantic water, shown in red, protruding all the way up to Svalbard, sort of fighting against the cold water masses of the Arctic Ocean and the sea ice that is drifting out on the opposite side of the Fram Strait. So this is the area we'll be zooming into in a while, but I'll dive deep into a fjord first and talk about tidewater glaciers. And this was briefly presented by Ankit Pramanik yesterday. Tidewater glaciers are glaciers that actually end in coastal waters, in a fjord or along the outer coast. In Svalbard, this will typically be 50 to 100 meters deep or underwater, whereas in Greenland or in Antarctica, they can be hundreds or even thousands of meters deep. And what happens is, in the main melting season, you will have lots of fresh water coming out at the front of the glacier, and since it's fresh water being injected into salt water, it will be very buoyant and rise rapidly. And during this rise of fresh water, it entrains lots and lots of ambient water, so that the volume you get up towards the surface might be 100 or even 1,000 times more than what you actually inject. And because of this, it acts like a suction pump for organisms in the water column, so that feeders can aggregate in large numbers in front of these glaciers. So an example of this is shown in front of one of the glaciers in Sundfjord, where you see thousands of birds aggregating, just eating what is coming up from the deep with this glacier front plume. So what we have seen in recent years is that as sea ice is retreating and the sea ice season is much shorter, a number of animals and birds are using the glacier fronts as a habitat and a feeding ground instead of using sea ice. So it is kind of a refugia for Arctic species or sea ice species. Other examples are seals. What you see over here is a seal swimming in murky, sediment-laden glacial water. It's marked with a satellite tag, and by following a number of these, you can see how they actually congregate in front of the glaciers to feed, and hence their habits of living adapt to this changing environment with less sea ice. We see a similar picture for several bird species that usually like to be around sea ice to feed. When the sea ice is gone, they fly away to glacier fronts instead. So this is a couple of ivory gulls that were nesting over here, and when the sea ice was all gone, the male in red would fly over this way, and the female with the white dots flying towards the glaciers further north and east. So there's good reason to look closely at how these glacier hotspots are functioning. But there's too much text here, but it's an attempt to summarize the needs that we have for data to understand how this plume varies and what controls it. You need to know how the glacier provides meltwater in time and space. So how is the water channeled and what controls how much is coming out? And the second thing you need to understand is the fjord itself. How much warm water is there? How many organisms are there? How does that vary, and how is that influenced by the glacial runoff? So the starting point is close to the glaciers, and we thought it would be a pretty straightforward study to understand how it works. We had some seal-collected data, so seals with CTDs that collect temperature and salinity data. That's shown on the left here, with salinity on the bottom axis and depth over here between 0 and 100 meters. And what it shows right next to the glacier front is that there is extremely low salinity for a marine environment, so the seals are actually diving inside the plume of the glacier with fresh water to feed on what's there. And in these two panels over here, we try to reproduce that in what is called a non-hydrostatic model. That's a really high-resolution model that does a fantastic job of mimicking what the water actually does. And we do manage to reproduce very similar profiles using different values for runoff and different values for the depth of the discharge, etc. So we can produce a range of such scenarios. And these, in turn, can help us provide input for larger scale models. It tells us how to introduce the freshwater into a larger model. So these fine resolution models are simply too computationally expensive to run for a fjord or a larger region. So we need to use the output from this to learn how to put it into the other model. So having experimented a bit with this, we can now introduce freshwater in a way that mimics the near field. That was the most complex slide I think I had. So this one then shows a fjord model. Now it's a 3D model, so it has Sundfjord and the main glaciers in here, and it starts at the beginning of the melting season for the glaciers, and the blue colors are fresh water coming from the glaciers and then moving out of the fjord. And that's a fine tool. It tells us how the fjord works, and if you look at it not from above but in a vertical transect, you can learn about how the Atlantic water from outside here can protrude towards the glaciers, etc. So you can play around with this a lot, and before you do that, you should validate it and check model results for example, a time series from a mooring for 1 year to see if the temperatures you get in the model compare well with more time series. So as was presented at the beginning of this session, long time series are really important for modeling, and also shipborne data or data collected by seals or gliders or other autonomous platforms. So that's that model for that fjord, and we can provide glacier runoff data for that fjord because we have a lot of people working hard to collect glacier mass balance data from that fjord, but we don't have that from all fjords and all coastal areas. So if we want to do a regional exercise to look at how freshwater circulates around this area, we need a glacier mass balance database for all of Svalbard. Unfortunately, because there are a number of institutions working in different regions, and some people are making models both of the terrain, as is shown here, glacier distribution, the terrain of what is below the glaciers, and you combine that with weather models to make a runoff model. In the end, you can actually distribute, as is indicated here, where the largest runoff points are. Now, once you have that, you can move on and produce a regional model. And then you can look at the aggregated freshwater that comes out of all of the glaciers. Now, why do we need to do that to understand that first glacier front? That's because the weather above the glaciers are significantly influenced by the sea ice cover around this larger area. And I don't know if time is going to allow it, but towards what you see in blue here again is freshwater. So in the beginning there was sea ice melting in spring. Now you see freshwater coming out from all of those different glaciers, and a circulation is set up around the entire group of islands. Towards the end of the year in winter, a lot of that freshwater ends up over here. And it just so happens that this area is one of the last areas in this Svalbard region that has a significant sea ice cover in the last years. That is connected to several things, but one of them is the presence of seawater. So water from the fjords over here ends up on the east coast, helps produce a sea ice cover, and that is one of the things affecting the winds going from east to west. If you have a lot of sea ice here, you will have colder air coming over the glaciers. If you have open water, you will have hotter and more humid air coming in, and this influences the entire snow balance in winter and the melting rates in spring and summer. So moving back into Kongsfjorden, it's one of those areas that have lost a lot of glacier area in the last many years. This shows how glacier fronts have retreated since mid-1800s until this year being way back here. And that's not untypical for Svalbard. It's, that's how it looks for most of the area. Now we've had a couple of years of campaigns with helicopter-borne radar. So we look at the thickness of the glaciers and what is below the glaciers. So this is where the glacier front was in 2015 or so. And by doing these radar measurements, we can actually look at where the glacier will be when it retreats further. I'll jump to this one actually. This is what your Kongsfjorden is going to look like in a few decades when the glaciers retreat even further. And our ultimate goal is to be able to have some prediction on what this is going to have of effects on the ecosystem. The glaciers will no longer provide this refugia for the species by aggregating food. Instead, all of the glacier water, because there will still be glaciers around, this glacier meltwater is going to come out as rivers in the surface, so it's going to alter the stratification completely, and it will no longer be a pump in the same way as it was. On the other hand, the fjord is going to be much larger. It's a longer fjord, so we will have more tidal exchange that's going to increase mixing and have opposite effects that can actually increase the vertical nutrient exchange, etc., which could, at least theoretically, increase the productivity in the fjord. So the only way to try to make predictions of what the future Kongsfjorden or other similar areas are, the only way to do that is by understanding the system through a suite of models, calibrating them against data from ocean, sea ice, atmospheric glaciers, and then you can try to produce your future model. And that's what I had to say.
Thank you.